Okay, so you're going to be looking at Dirac's theorem, and Dirac's theorem basically says if G is a simple graph with an order greater than or equal to 3, and the minimum degree value of all your vertices is n over 2, then G has a Hamiltonian cycle. So the first thing we're going to look at is firstly what is A and what is B. So the conditions here is it's a simple graph, has an order greater than 3, and all the minimum degrees, or the minimum degree of any vertice in the graph is greater than or equal to n over 2. Then it's saying if that is all the case, then G has a Hamiltonian cycle. Before we begin trying to figure out how exactly to go about proving this, let's just actually write this down a little bit differently by showing you what exactly all the conditions mean and then what exactly it means to be a Hamiltonian cycle in this case. So first of all, if it's going to have a Hamiltonian cycle, well, you know there's going to be a path involved. So let's start off with talking about a path utilizing the green, conditions. So we say, okay, let P be the longest path in this graph. Okay, so let P equal to x1, well, no, let's use v1, equal to v1, v2, etc., all the way to vk, be the longest path in G. Now, if it's the longest path, it can't be extended. So you can't get a longer path. And that means that all the neighbors of V1 are in this path and all the neighbors of VK are in this path. Okay, so since the way that we've written this, we said it's the longest path, since P is the longest path, all the neighbors of V1 are in the path, and all the neighbors of VK are in the path. If they weren't, we could have just added them to the path. So say, for example, you had V1 there, V2, V3, V4 kind of thing. V1, V2, V3, V4, and I don't want to use purple. So say you had this, and say this was just your longest path, and you had V1, V2, V3, and let's just say VK, just so that you can see what we're talking about. If, say, V1 had a neighbor that wasn't in the path, it would have been like Vx, for example. We could have, and you had this path situation happening here. If Vx was a neighbor of V1, that means that there would be an edge between them, which means we could actually just extend this path. And that's why we can say that. So since P is the longest path, all the neighbors of V1 are in the path, and all the neighbors of VK are in the path, because similarly, you can do it for VK. So you could have had like a VT situation here that happened to have an edge if it's a neighbor to VK, and that meant you could have extended your path. Okay, so we know that aspect. So all the neighbors of V1 are in the path, and all the neighbors of VK are in the path. Now, some of the other things we know about this is we have a minimum degree of greater than or equal to n over 2. So we know how many neighbors, V1 have. So we can say, okay, for VK, there is a set number of vertices which are going to be adjacent to VK, and that is going to be greater than or equal to n over 2. So because we have the longest path and all the neighbors of V1 are in the path and all the neighbors of VK are in the path, there are at least n over 2 vertices which are adjacent to VK. So there are at least n over 2 vertices in the path adjacent to VK. We also know that the same thing happens for V1 because V1's degree is also greater than or equal to n over 2. So we know there's at least n over 2 vertices in the path adjacent to V1. Now we can actually go and we can say, okay, any of the vertices adjacent to VK are going to either be your V1 or, your V2, your V3, etc., all the way to VK minus 1. Because the only one that it's not going to be adjacent to is VK itself. Okay? Then, so out of this group, there's at least n over 2 of them. And out of this group, so here we start off with V2 because V1 is the one we're looking at here. So V2, V3, etc., all the way to VK are possibilities for being adjacent to V1. Okay. Now we're thinking about it has a Hamiltonian cycle. So those are just the G conditions, not the green conditions, which are your A's, A and then implies B. So we have now just the conditions that actually gave it to us. Then it says, okay, G has a Hamiltonian cycle. So what exactly is that saying? So let's just quickly explain the part where it says G has a Hamiltonian cycle. What exactly is that saying? It's saying there is some value, and we're going to refer to this value as J, and where J is between, 1 and K, such that there is kind of like this overlap that's occurring. In other words, Vj is adjacent to your Vk, and your Vj plus 1 is adjacent to your V1. Because remember, we're looking for a cycle. So let's just first look at the most basic case. So we have V1, and let's just say I have order 3 kind of situation, and we have Vk there. This is Vk minus 1. Technically, this is, 2 and 3, but I'm just trying to keep up with the subscripts we're utilizing there. And we have this path. So the path goes from V1 to Vk minus 1 to Vk. Now it's saying that there is some J is adjacent to Vk, and J plus 1 is adjacent to V1. So this is technically Vj, and this is Vj plus 1. And what it's saying is, okay, Vj is adjacent to Vk, which is true here. We have, that kind of edge. But it's also saying that V1 is adjacent to Vj plus 1. In other words, it's got an edge connected to Vk. And you can see the moment we drew in that edge, you can actually see the cycle pretty clearly, kind of a situation. So there you have your cycle. So let's just extend this, to more vertices. So again, we have V1. It continues on until we have some Vj. We have some Vj plus 1 happening there, and it continues on to Vk. And again, it's saying that our V1 is adjacent to our Vj plus 1, which means there's an edge over there. And it's also saying that our Vj is adjacent to our Vk, so there's an edge over there. And this allows us to have a cycle because we can go a nice like figure 8 kind of style that spans all the vertices of this longest path. Okay, so we're going to prove this indirectly, which means we need to assume that the negation of B is true and find a contradiction. So just a reminder, what exactly is B in this case is G has a Hamiltonian cycle, and we can write this as there is some J which is between 1 and K such that Vj is adjacent to Vk and Vj plus 1 is adjacent to V1. So we're going to assume that this is untrue. So let's just write the path again. So we have V1, dot, 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 kind of a situation, ends up at Vj. Vj is connected to Vj plus 1, dot, dot, dot situation, and it goes to Vk. So that's the path that we have, and it's the longest path. Now, previously, we said that we had Vj is connected to Vk, and we had Vj plus 1 is connected to V1, and by doing that, we have a cycle. Now we're assuming that there is not an overlap situation occurring. So we're assuming this cannot happen. By that we mean we don't have this, or we don't have that, or we don't have both of them. Okay, so the easiest one to visualize usually is the case where we don't have both of them. So if we don't have both of them, we have this path. So we have V1, again going to Vj, Vj going to Vj plus 1, continuing on to Vk. So we have that path. If we assume that Vj is not adjacent to Vk and Vj plus 1 is not adjacent to V1, that means that there is a degree of V1 vertices which are not adjacent to Vk, and that means that there is, a degree of Vk vertices which are not adjacent to V1. Now, if you look at that case, you're going to have, okay, you have one vertice there plus degree of V1 vertices, which are not adjacent to Vk, so you can't get that overlap situation, plus the degree of Vk vertices, plus that leftover vertice. Now, you know that the degree of V1 is greater than or equal to n over 2. You know that the degree of Vk is greater than or equal to n over 2. So suddenly you're sitting with more than n vertices in your path. So you have a greater than or equal to, here you have n plus 2 vertices in your path, which means you have n plus 2 vertices in your order n graph, which is a definite contradiction. Okay, but there are other ways to assume that this is not true, and that is just saying if Vj is not adjacent to Vk, that breaks it, because you can still say that Vj plus 1 is adjacent to V1. So let's look at that situation. So if we look at that situation, let's just rub this out so you can see it on the path. It's taking a little bit longer than expected to rub out. Okay, so we have our path, and we're just going to assume, so we're no longer assuming that both of them, let's just assume that the green one does not exist, so that Vj is not adjacent to Vk. Okay, and if that's the case, so we have, well, we can have an overlap of vertices connected to from V1 adjacent to Vk. So we have one overlap, a singular overlap. Okay, so here we're assuming that Vj is not adjacent to Vk, but Vj plus 1 is adjacent to V1. Therefore, one vertice is adjacent to both. So previously we assumed that there were no vertices that were adjacent to both V1 and Vk. Now we're looking at a more narrower scope where we're looking at there is only one vertice which is adjacent to both. Okay, so let's look back onto our path. So we have Vk is, by itself here for a second. And then we say that there are degree Vk of them that are not adjacent to V1, because we're saying that Vj is not adjacent to Vk. Okay, so Vj is not adjacent to Vk, so up until here there must be degree Vk of them kind of a situation occurring, which is not adjacent to V1. So it stops at that point there. But then you still have all the vertices which are adjacent to V1, including V1 itself here in this situation. So now you have the degree of V1 vertices which are adjacent to V1, but in this degree of V1 vertices, this Vj plus 1 sits as well. So here you have your V1 plus your degree of V1, but inside your degree of V1 is your Vj plus 1. And then you have your degree Vk, which also includes Vj plus 1, plus your Vk. So when you're adding this up, this is not actually the total right now because your Vj is counted twice. So when you look at this, you need to consider the fact that when you're looking at this, you have your V1 sits by itself kind of situation, all the vertices connected to V1 plus a degree Vk, and that's going to give you the total number of vertices in your cycle, or in your path, sorry. Is going to equal to that. But now you know that you have 1 plus greater than or equal to n over 2, greater than or equal to n over 2, so you're going to get greater than or equal to n plus 1 vertices. So again here you have more vertices in your path than you actually have in your graph, which is a contradiction. Okay, just a reminder here of when I ended up writing it like this, where I said V1 plus degree of V1 plus the degree of Vk, take into account that because the way we made the assumption, your Vj plus 1 is included in both of those. So we would have had 1 plus this 1 here, plus greater than or equal to n over 2, plus greater than or equal to n over 2. And the reason why we don't have that additional plus 1 situation here, because we subtract this one out of there so that we're only counting the vertices in our path. And when we do that, we have degree of Vk minus 1, so we have those leftover vertices kind of situation, plus the one from the Vk, and then it narrows down to the 1 plus greater than or equal to n over 2 plus greater than or equal to n over 2. So just be very, very careful, particularly when it comes to the way that a lot of people write this. This line over here is not actually accurate. What is happening is when you are looking at the number of vertices in your path, your degree of V1 includes Vj plus 1, and your degree of Vk includes Vj plus 1. So when you go and work this out, you're actually having to subtract, because your Vj plus 1 is being counted twice, you need to subtract it. And then when you do that, you have your minus 1 plus 1, and that gives you a 1 plus or minus plus greater than or equal to n over 2 plus greater than or equal to n over 2, which gives you n over 2 plus 1 vertices, which is also a contradiction. We're not actually done yet, because what we've proven is we went through this process of there is some j, where j is between 1 and k, such that Vj is adjacent to Vk and Vj plus 1 is adjacent to V1. So we have shown that there is a contradiction if we assume this to be untrue. So we showed that this was a contradiction if assumed to be untrue. And when we did this, we showed that if this was untrue, we would end up with a path which has more vertices than the graph. So what we've shown so far is that there is a cycle. Okay, by the assumption where we assume this to be untrue, we've shown that there was a path with more vertices than the graph. So we now know there is a cycle. So we now need to show the Hamiltonian part, which means it spans all the vertices in the graph. Okay, this gives us a cycle, and let's just go back to our drawing of this. So we had V1, continues on to Vj, continues on to Vj plus 1, continues on to Vk. We have this one connected to this one like that. This one connected to this one like that. So when we have, our cycle, we have this kind of thing occurring. And we are going to go through writing the description of this cycle. So say we start at V1. So we're starting over here at V1. It goes from V1 to Vj, right? Then it's going to go from Vj to Vk, then from Vk to Vj plus 1, and Vj plus 1 all the way back to V1. So we have a cycle. We're just going to call it C bar. We say V1 dot 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 to Vj, Vj directly connected to Vk, and then we have, it goes down, so we have Vk minus 1, just to show you your order situation. And then we go to Vj plus 1 to V1. So that's our cycle of length k. Now we need to look at, does it contain all the vertices of the graph? So we had shown earlier that, when we went through this approach and we went through just utilizing the conditions of n over 2 and stuff like that, it would perform a contradiction. Now we need to show that it actually does contain n vertices, basically. So we say if the graph minus the cycle is not empty. If it's not empty, that means there's some vertices left over which are in the graph which aren't in the cycle. Then there must be some vertex V, which is the element of G minus the cycle, that is adjacent to some vertex Vj. So I'm just going to rename this. So let's just call this X for a second. So there's some vertex X which exists in the graph which does not exist in the cycle. But we know based on the fact that every single vertex has a degree greater than or equal to n over 2, there must be some vertex in that cycle which is adjacent to it. So some random vertex we can refer to where it's adjacent to it. And if that's the case, we could have made our path longer. Just by the idea of, when we were creating the path, if you go back to how I described that. So we say, but then we could attach the vertex to the path ending in xj. In other words, we rename our ending in vj. We rename our path so that it sits, at the end, and then we can do what I described earlier, where you can, if it's adjacent, you can add to it, and then it creates a longer path containing the k vertices, creating a longer path, which is again a contradiction to, everything that we've done. And therefore, all of G are contained in the cycle. All of G are contained in the cycle. making the cycle a Hamiltonian cycle.